right, this is video 16C. The objective for today is to understand sound. We're going to introduce sound, and then there's a sound lab. So anything about assignments or announcements, go ahead, check the just check the introductory video. So the big question for today is, why can no one hear you scream in space? All right, so remember there are two codes in each video. One will be written and the other will be verbal, said by myself. Each code will be 3 numbers. You will need all these codes in order to move on with the homework assignment. So write what is in green. Both honors and physics will need this in their notebooks, and this is the video 16C written code. I would recommend writing this down somewhere. All right, so back to the original question, why can no one hear you scream in space? So sound is a mechanical wave, which means the energy is being transferred through a particle-to-particle interaction. It is a longitudinal wave, and it is a pressure wave. Sound is differences in pressure. We can measure and graph these differences in pressure. That's what microphones do. So differences in frequencies in sound are often referred to as pitch. Humans can hear on average 20 hertz to 20,000 hertz. Ultrasonic is more than 20,000. Infrasonic is less than 20 hertz. Young people can hear the higher frequencies. So you can see what sound is in that simulation, and that's why you can't hear anything in space, because there's no medium to travel through. There's no air for it to travel through. So we're going to calculate the speed of sound using just some simple lab equipment. So waves can interfere with each other. Constructive interference occurs when two crests meet. Destructive interference occurs when a crest meets a trough. So you can see that in the simulation. So sound waves can interfere with each other in concert halls. If designed poorly, there can be dead spots where sound cancels out. So you can see that in this simulation. Now beats are when two sound waves of different frequencies approach your ear. The alternating constructive and destructive interference causes the sound to be alternatively soft and loud. So you can see that beats in that simulation. Notice the difference in frequencies is the frequency of beats. So let's talk about the Doppler effect. The Doppler effect is an increase or decrease in the frequency of sound, light, or other waves as the source and observer move toward or away from each other. The effect causes sudden change in pitch, noticeable in a passing siren. You've probably experienced this in a car as playing loud music and is going really fast by you. The music will sound just a little bit weird before and after it passed you. This is because waves are being compressed or stretched. This happens at my favorite place, the Indianapolis Motor Speedway. All right, so now a sonic boom. A sonic boom is a shock that is produced by an aircraft or other object flying at the speed equal to or exceeding the speed of sound. And that is heard on the ground as sound like a clap of thunder. So just try to figure out what the first sonic boom was, the man-made one. A wave reflection is when a portion of the wave bounces and returns, and a portion of the wave undergoes transmission across the boundary. Echoes and reverberations are examples. So refractions of sound waves. Refraction of waves involves a change in the direction of waves as they pass from one medium to another. Refraction, or bending of the path of the wave, is accompanied by a change in speed, direction, and wavelength of the waves. This is why sound travels better at night. Sound travels faster in the warmer air above the surface and gets refracted back down to the surface. So the natural frequency of an object is the frequency or frequencies at which an object tends to vibrate with when hit, struck, plucked, drummed, or somehow disturbed. This is how music is generated, by manipulating the natural frequency of the instrument. A resonant frequency is a little different. A resonant frequency is a frequency that causes resonance. So resonance is a phenomenon in which an external force or a vibrating system forces another system around it to vibrate with greater amplitude at a specified frequency. Usually natural frequencies and resonance frequencies are the same. So this is how music is formed. So we're going to do the wine glass music lab. All right, so now we're going to talk about standing waves, the vibration of a system in which some particular point remains fixed while others between them vibrate with the maximum amplitude. Nodes are fixed, antinodes are the maximum points. A harmonic is an overtone accompanied by a fundamental tone at a fixed interval, produced by vibration of a string, column of air, etc., in an exact fraction of its length. You can see a lot of these are a lot of music links for that. All right, so then we're going to do the Whirly Tube lab. That will demonstrate sound. So those are the links for that day. I'll go ahead and give you the verbal code. The verbal code is 843. I say that again. The verbal code is 843. And as always, I'll leave you with this. There's too much unknown in the universe to take a break from learning. Get out there and question everything.